For most of the last decade, Pluto has been treated like a closed case, a dwarf planet demoted, photographed once by a passing spacecraft in 2015 and quietly filed away as a problem astronomy had already solved. Distant, cold, done. But in the summer of 2026, something changed. A signal buried in infrared light, invisible to every instrument that came before. It surfaced from data collected billions of kilometers away. It didn't match anything in any catalog, not on Pluto, not anywhere. And the moment scientists confirmed it wasn't a glitch, wasn't noise, and wasn't anything they'd seen before, Pluto stopped being a closed case. Tonight, we're looking at what the James Webb Space Telescope actually found out there, why it took nearly 5 decades of technology to see it, and why the discovery is quietly unsettling planetary scientists who thought they already understood this world. To understand why this matters, you have to go back to what we thought we knew about Pluto in the first place. In 2015, NASA's New Horizons spacecraft became the first and only mission to fly directly past Pluto, sending back the crisp, visible light images that finally ground telescopes and even Hubble could never fully reopen it. Pluto is small, faint, and extraordinarily far away. And both instruments are built primarily for visible light, the same kind of light your eyes detect. Visible light is good at showing you shape and color. It is far worse at showing you temperature, composition, and the subtle chemical fingerprints hidden in a surface's heat signature. To really understand what Pluto is made of and what's happening on it right now, you need a different kind of eye entirely, one built to see heat itself. That eye is the James Webb Space Telescope, and its instrument built exactly for this job is called MIRI, the Mid-Infrared Instrument. In May 2023, Webb turned MIRI toward Pluto and Charon and did something no instrument in history had ever done. It captured a high-quality mid-infrared spectrum of the Pluto system, spanning wavelengths from roughly 5 to 27 micrometers. That range had never been explored on Pluto before, not because scientists didn't want to look, but because no earlier telescope had the sensitivity to do it from this distance. It's the difference between glancing at a house from the street and finally being able to read the electricity meter on the side of the wall. The light curves Webb recorded, tracking Pluto's brightness in infrared as it rotated, revealed variations tied directly to what different regions of the surface are made of. Methane ice here, water ice there, dark organic deposits somewhere else, each holding heat differently as they turn through daylight and shadow. When the results were finally published in April 2025 in the journal Astronomy and Astrophysics, and again in June 2025 in Nature Astronomy, a team led by researchers from the Paris Observatory and CNRS laid out something that surprised even them. Pluto and its largest moon, Charon, don't just look different. They behave thermally like two entirely different worlds, locked in a strange, ongoing exchange. Webb's data confirmed that material is actively being pulled from Pluto's thin atmosphere and deposited onto Charon's surface, staining its poles with dark, reddish deposits. It's an interaction that, according to the researchers, happens nowhere else in the solar system. Two bodies, tidally locked, permanently facing each other across 12,000 miles of space, one slowly bleeding its atmosphere onto the other, like breath fogging a mirror. That alone would have been enough to call the mission a success. But it wasn't the end of the story. It was the setup. Because in July 2026, just weeks before this video, a new analysis of Webb's infrared data turned up something that doesn't fit into any of the categories scientists had prepared for. Researchers studying Webb's observations of Saturn's giant moon Titan noticed an unexplained dip in the infrared spectrum, a specific wavelength where light was being absorbed by something on the surface that didn't match any known molecule ever catalogued, not on Titan, not on any other body in the solar system, and not in the exoplanet spectra scientists have used as reference libraries for years. The missing wavelength sat at almost exactly 511 micrometers, a precise, narrow, unmistakable gap in the light. On its own, that would already be a notable mystery. But then the team did something almost as a formality, a routine comparison. They went back into Webb's archival observations of Pluto, the same May 2023 dataset that had already reshaped our understanding of the Pluto-Charon system, and checked whether the same absorption feature appeared there too. It did. The exact same wavelength, the exact same signature of a molecule absorbing light in a way nothing else in the solar system does, present on two worlds that could not be more different from each other. Titan, a moon of Saturn wrapped in a thick nitrogen-methane atmosphere, warmed faintly by a haze of organic smog. Pluto, a dwarf planet at the edge of the solar system, 4 billion miles from the sun, with a surface so cold that nitrogen itself freezes solid. Two bodies separated by over 1 billion kilometers. Different sizes, different orbits, different histories, and yet both are marked by the identical chemical fingerprint. Something Webb had never seen before on either of them until now. Scientists ruled out the obvious explanation first. If the signal came from the atmosphere rather than the surface, it should behave differently. Depending on where you look, growing stronger toward the edge of the disk, where sunlight has to pass through more gas to reach the telescope. Researchers tested exactly this on Titan by comparing the spectrum from the center of its disk against its edges. The signal did the opposite of what atmospheric absorption should do. It grew weaker at the edge, not stronger, which means, according to the team's analysis, the absorption isn't coming from something sitting directly on their surfaces. So what is it? That's the uncomfortable part. Nobody currently knows. It isn't methane ice. It isn't water ice. It isn't any of the organic tholins, the reddish-brown compounds already known to color both Pluto's terrain and Titan's dunes. Researchers have proposed it might be an undiscovered organic compound, something built from the same basic chemistry that produces the building blocks of life, but arranged in a form we've never directly measured before. Not in a lab, not on Earth, not anywhere else we've pointed a telescope. If that turns out to be correct, it wouldn't just be a curiosity. It would mean the raw chemistry capable of producing life's ingredients is more common, more varied, and more widely distributed across the solar system than any model currently accounts for. This is where the story becomes less about one dwarf planet and more about a pattern. For decades, we treated distant, icy worlds as essentially inert, frozen relics, too cold for anything interesting to happen chemically. Webb's infrared vision is quietly dismantling that assumption world by world. First, it revealed that Pluto and Charon are locked in an active atmospheric exchange, unlike anything else observed anywhere. Now it's revealing that Pluto and Titan, two worlds with almost nothing in common except distance from the sun, share a chemical signature so precise it cannot be coincidence and so unfamiliar that it currently has no name. There's a reason no one caught this before Webb. Earlier infrared instruments, including those flown on previous space missions, simply didn't have the combination of sensitivity and spectral range needed to isolate a signal this faint at a wavelength this specific, especially from a target as distant and dim as Pluto. It took a telescope sitting nearly 1 million miles from Earth, shielded from the sun's heat by a 5-layer sunshield the size of a tennis court, cooled to nearly absolute zero, to finally be quiet enough, in an instrument sense, to hear this whisper of chemistry at all. NASA's next chance to dig deeper is already scheduled. The Dragonfly mission, a rotorcraft lander designed to fly across Titan's dunes and lake beds and sample its surface chemistry directly, is set to launch later this decade specifically to answer questions like this one from the ground. Researchers now hope Dragonfly's direct measurements at Titan could finally identify the molecule responsible for the 5.11 micrometer signal, and by extension, help explain what's sitting on Pluto's surface as well, 4 billion miles further out, where no lander has ever been sent and none is currently planned. Until then, the signal remains exactly what it's been since researchers first isolated it, an open question written in light, present on two of the strangest and most distant worlds we've ever studied, and unreadable by anything humanity has built so far. What Webb has shown us is that Pluto was never really a closed case. It was a world we photographed once in visible light for a matter of days, and then assumed we understood. Infrared light told a different story, one written in heat rather than color, and it's a story we've barely started reading. Somewhere in that 5 micrometer gap in the spectrum is a molecule that doesn't have a name yet, sitting on the frozen surface of a world we once dismissed as finished business. And whatever it turns out to be, it's already proof of something bigger. That the outer solar system isn't the quiet, frozen archive we assumed it was. It's still full of chemistry we haven't identified, processes we haven't explained, and questions that a spacecraft launched decades ago never got the chance to ask. If you want to be here when scientists finally figure out what that signal actually is, subscribe and turn on notifications, because this is a story that isn't finished, not even close, and the next update from 4 billion miles away might rewrite what we know about Pluto all over again.